module demonstrates the connection between two modules. You can see that here, what we've built in order to demonstrate that. And in fact, that is Thomas Navikas here standing in front of the device, which now is nearly completed. So I'm very, very proud how fast this has been going on. Now I've shown you what we do in my research group in order to do this. And I always speak of 1 million and 1 billion in this talk, and some of you guys must think, wow, he only has around 4 or 5 or 2. How is he really going to ever go from these small numbers to these really large numbers? And I think your query is well placed, or your doubt is well placed. And what we need to do is we need to really now start manufacturing these things. We can't have PhD students with soldering irons and wire bonders putting this together. So now we're trying to make the next step now to really manufacture these devices. And so what we've started last year, at the end of last year, a company, and I can say, I'm not allowed to say the name, it's called Universal Quantum, and with the goal is to manufacture practical and large scale quantum computers. So the idea is really to build practical quantum computers, not to work in insulation, also work on the software. This is really, really hard stuff, what I'm telling you about. It's really, really difficult. And I wish only the hardware would be easy, difficult. Sorry. I wish only but the software is just as hard. And doing all the control of all these ions, imagine like having these quantum computing modules, running the error correction, all of this is very, very difficult, and map this to practical problems. So this company really will work on the whole range of things, from the low-level software, some application developments with partners, and particularly on manufacturing these quantum computing modules. So we are right now at the starting point, so don't expect yet a quantum computer manufacturer tomorrow. We are working with investors currently, and we're looking for a site for the company. But let me tell you maybe a bit, again, what makes us different to maybe competitors, to Google or IBM. So as I said in the starting point, our technology is a room temperature technology, or mild cooling. So 70 Kelvin is very close to room temperature in terms of technology requirement, really. There are eye-trapping quantum computing companies out there already. We don't try to compete with them. We develop quantum gates executed using RF and microwave radiation. That's the same technology as you use for your mobile phones. And so we develop technology to execute microwave quantum gates, and that will then replace the need for having to align eventually millions or billions of laser beams. There are approaches for quantum computers with trapped ions using photonic interconnects. There's a very famous approach at Oxford University, known as for the 2020 engine. Again, we don't believe we want to go down that way. Our company will work on electric field connections for modularity. We believe the fact that we can have these much larger connection speeds will really help in getting very fast to practical large-scale machines. And the approach is modular, allows variable connectivity, but most importantly, and that's really most importantly, it is simple. And I think that's really, really important in order to do this. So I know that some of you guys might be interested in, I don't know what just happened. Just lost my...
That's classical computing for you.
Absolutely, yeah. So, good. So if you're interested in this, if you like to get involved, we will have at some stage a significant recruiting exercise. Not quite yet, but I have an email address for you here. Please do not expect a reply so we are literally having this update to just gather interest for people who obviously you can imagine we're looking for a wide range of skill there, and this is really only just to register interest if you're interested, and so please don't have your expectations high on an immediate reply. And obviously if you're a big company, you want to partner with us, or investor, and have a few million pounds to spare, then obviously you can also get in touch with us on the investor side. So that brings me to the end of my talk. So let me summarize what I wanted to say. So I think we're very optimistic. It's possible to build a quantum computer with trapped ions. It's still really, 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 really hard. So it's not easy at all. But I think we've got some really great engineering solutions in order to have a good shot at actually really building a real machine. So we've built a demonstrator device at the University of Sussex, which is now nearly completed. I've shown you some pictures. People always ask me, so when can you break RSA encryption? That's a really hard question, and to be honest, any answer I'll give you will be most likely terribly wrong, so I'm not going to even say that. But I have this here, large-scale universal quantum computer, and I think that's kind of a quantum computer which has a quite sizable number of qubits, and please don't ask me what exactly sizable is defined as. That is always my easy way out here to not blatantly fail but not reach these numbers. So I think quantum computers offer a tremendous chance, and there is obviously applications in the financial sector and across all the sectors, and they are very important. But what blows my mind away is really the possibility to simulate other physical systems, like to think things about drug discovery, doing things you could never do before, and maybe leave a mark in the world, leave a mark if we can actually build such a machine. And that's what, in a way, gets me to get up in the morning. So I think it's really a fantastic opportunity, and I'm the luckiest man ever to be able to be playing a small role in this. So if you want to hear more, here's some websites, and I've written a chapter in a book. If you're not bored yet of me speaking, have a look at it. With that, thank you very much.